This project was about the procurement of a new traffic management system for 2 of the subway lines in the Stockholm Metro. So the red and the blue lines in this drawing here. And there were some challenges in this because this new system needs to integrate with a very old existing signaling system that controls the safe movement of the train in the subway. So these existing interfaces were not very well documented or so they wanted to do a digital twin of the existing system to define clearly these requirements on the interfaces and everything to be able to procure this system in an efficient manner. So the current architecture, or the old architecture that they're going to replace, looks like this. So the train or the traffic management staff that controls the traffic, they use a very old system, which is basically a physical panel with push and pull buttons where they can request different train movements, and they have physical lamps that indicates on this board where the trains are and so on. This is connected to a set of relays that adds additional logic and provides some very basic automation in the system. So you might have predefined rules for how to turn trains at the end of the line and so on. And these relays that are shown in the middle here, they are not really safety critical. So it's just additional functions. And then at the bottom, you have the really safety critical part of the signaling system. So that basically ensures that the train will not run into the same area and they will not run over points or switches that are not in positions and so on. So basically taking care of the safe movement of the train. And these systems are like 50 years old or something, so they're quite dated. And they want to move to a system that looks more like this. So these control panels will be replaced by a modern computerized traffic management system. And the relay system that is this middle layer will be replaced by computers or PLCs with the idea that they should, in principle, preserve the functionality of the old relay-based system. There will, of course, have to be some changes that also needs to be investigated on the digital twin level. But then these safety critical part of the signaling system, which are these old relay rooms, those shall be left completely untouched for the time being. And the main reason is for that is that it's very costly to touch, and even if you want to make a small changes to this safety critical system that has been assessed and approved, there's a big overhead in getting safety approvals and everything for doing that. The other things you can more easily change since they're not directly safety critical. So that's the main idea here. And the goals of developing a digital twin for this is that you want to, before you go out and tender the system, you want to understand if there are particular dependencies in the different parts of the existing systems that needs to be documented and perhaps preserved or addressed. There could potentially also be safety critical functions that are dependent on this exact design. So maybe it isn't as modular as it was intended to be. You can, of course, also with the digital twin try out this concept and play around with it and produce detailed specifications for the tender, in particular on these interfaces and what the functionality each subsystem shall have. Then you can, of course, also use the digital twin when you develop the new system because you have something to test against, and you can even use it in the future when the new system is installed for making upgrades and so on, though that was perhaps not the main purpose at this stage. So the process that we use to develop this digital twin in itself is a bit interesting, but I won't have the time today to go into that. It's based on something called formal methods and design automation. So it's basically an efficient way of developing systems from formal specifications and configuration data. So we started off by applying this to develop a digital model of the existing system. Then replaced these non-safety critical relays by a PLC program that was generated from these specifications. And in each step here, we apply simulation to test it and something called formal verification to verify the safety, basically mathematically proving that the safety requirements are fulfilled in each step here. Then we built a completely digital model of the future system, all in software. But then in the next step, we replaced the model of this PLC with an actual physical PLC. And finally, we also installed that in the field, connecting it to the actual relay-based signaling system. So this was all modeled with a tool that we have that's called ProverILOC, which is basically a tool for designing rail control systems and doing testing and verification. So the relay systems were imported by reading the relay drawings and turning those into software and logic to model them. And the 3 different components were modeled individually and were communicating over an Ethernet interface. Then the next step was this moving from the relays to the PLC. So there we did not just simply translate the relay drawings into PLC logic or software because we knew that there were going to be some changes introduced here since we're going to interface with a computerized system in the end rather than this control panel. So there we instead generated this software from the requirement specifications that we had developed. So that's a more flexible way because then you can change and add requirements and so on. And this PLC program could also be simulated and formally verified. So again, that was all done digitally, so running on 3 different simulated models connected together. And then it was also easy to replace this control panel model with a model of the new traffic management system. And in future, of course, when you build a new traffic management system, you can connect it here to test it with a model of the PLC and the signaling system. Then the next step was this introduction of a physical PLC running. So then it's basically the same thing. You can connect through various Ethernet interfaces and have it running on this PLC instead. And finally, the connection to the actual relay system had, of course, to be done in the field where this relay system is. So that was done overnight. And that's also one of the key benefits of this approach, that you can run all the tests beforehand, and then the actual installation and testing that needs to be done on site will be much quicker. Because obviously in a metro, you don't want to spend a lot of time testing on site because that means that you will have to shut down the operation. So there's typically very limited time for that. But of course, you have to actually physically wire the PLC inputs and outputs to these relays. So it's still a little bit of effort to do that. So what was the result of this project? Well, first of all, we established that it was a truly modular system where we could separate these 3 parts, and we could define these interfaces so that it will be easy to write the tender specifications, including these interfaces. We also showed that it worked to replace this non-safety critical relay system with an actual PLC. We identified some dependencies on these implementations, so new safety requirements were added to these PLC systems that weren't there before. And there was this transition into the physical environment where we connect this to the actual relay system was simplified since all the testing was done in advance. So we know that the functionality was correct before it was actually installed. And we used these formal specifications now that are validated with the simulation approach. So we know that what we have actually specified and can be put into the tender is actually what we need. And then, of course, going forward, we have this model that can be used in particular when you develop the new system to have something to test against during development. And you can connect it to additional physical components. And you can also use it during the life cycle of the new system to manage issues and reproduce error reports and running error logs and so on. And of course, try out any new functionality. In addition, you can also use it for training and such purposes. Yes, thank you. That's all for me for now.